But let's go to those review problems. Which one do you want to start with? Anybody have a good one to start with, and then I'll tell you if I want to do it or not, because it's really just about me in this class. That's a joke. Yeah? 135? You want to start 135? That's a good one, I think. Let me see. 135. So this would be a good one to do because we in this class have not talked about partial fraction decomposition yet. What's nice about partial fraction decomposition, and yes, I will tell you the downside to it is it's really only useful in some pretty specific cases like this one, right? The other thing about it is it's not actually that bad. Please believe me on this. Partial fraction decomposition is not that bad. One thing I've said before in this class is if you are working on a math problem, a great general strategy is try to break it down into smaller pieces, totally dominate those smaller pieces, and then put them together. It's much easier to be consistent when you attack a problem like that, and this is a perfect example of that. This partial fraction decomposition is also nicely set up for you because what has the denominator already been done? What's already been done to the denominator? It's already been factored. If we had studied this as an extended topic, I would have given you this in unfactored form, and then you would have had to use synthetic division to factor the denominator. You would have been a little angry at me for that because you don't like it, and then you would have to do more. The idea is all we're doing is breaking down. What type of integral is this? There's no limits of integration, so it's indefinite. It's going to be a plus C on this thing. This is an indefinite integral that we want to break down into three things. So our entire goal, everybody, is essentially to teach you right now a little bit more some algebraic maneuvers based around this. We're trying to take this 2x plus 3 over this nicely factored thing, and what are we trying to turn it into? Some constant over x plus some constant over x plus 2 plus some constant over, because if we do that, taking the integral of each of those pieces is relatively straightforward. How do you solve for A, B, and C? I'm going to show you the cleanest method and also point out why it's kind of strange that it actually works in my opinion, and then you can solve for why. You can have that annoying thing at the back of your head. It's been there for like 5 years for me. If we want to simplify this, what's a great thing we can multiply everything by if we wanted to simplify it? The what? Multiply everything by that denominator, what do we end up with? We end up with 2x plus 3 equals a times x plus 2 times x minus 1 plus b times x minus 1 plus c times x plus 2 times x, right? So it doesn't look like that's super helpful because you're like, man, I have x's and an a and a b and a c. And usually if you have 3 or 4 variables, you need 3 or 4 equations. In this case, you don't, because this statement has to be true for all values of x. So guess what you can do? You can just pick some nice values of x that collapse things away. And I've labeled these, I've personally called them magic numbers because they magically make it much more easy to do. So for example, a magic number could be x equals, how about 0? Why is x equaling 0 a magic number? Because if I plug in x equals 0, what happens? What does the left side become? 3. A turns into 2 times negative 1 plus, 0 plus 0. So therefore, what does a equal? Negative 3 over 2. You see that? So there are 2 other magic numbers. There better be. X equals what? 1. If I do x equals 1, you end up with 5 is equal to 0 plus c times 3 times 1. So what does c equal? 5 over 3. And then what's the last magic number we can use? So you end up with negative 1 is equal to 0 plus b times negative 2 times negative 1. Right? Is that correct? No. Negative 2 times negative 3. Thank you. That didn't look correct. Plus 0. So therefore, what does b equal? 1 over 6. So here's the thing. We're now effectively done because now what can we use those values? Where can we plug those in?
Back into
You can take these and plug them back in here, leaving you with, instead of a, what do you write? Negative 3 halves over x. And then what's b? 1/6 over x plus 2 plus 5 over 3 over x minus 1. Now here's the thing. All you're doing is integrating each of these. Are you pretty confident that you can integrate those things? Yeah, you can factor out the numerator, so these constants just kick out to the front. And when you do the integrations, what mathematical thing are you going to see 3 times? You're going to see what? It's even nice, the coefficients of x are 1, so you don't have to worry about the chain. But this is the setup. All partial fractions, it's not, you don't need calculus to do the partial fractions. In some math curriculums, actually in past years, when I was teaching Algebra 2 honors at my last school years ago, we would do this kind of math right here in Algebra 2 honors. Specifically because where do you end up seeing it? Calculus. This is not calculus level manipulation. But do you understand what I mean? You're like, he said that in a sinister way. This is actually kind of cool algebra. Now, here's the inconsistency that's bugged me for a long time, and you can think about it too. Here's the thing. Here's the original thing we're integrating, right? What were our magic numbers?
0, 1, -2.
Things that can kill things over here, right?
Yeah.
But here's the thing. Look at the original function.
They don't work.
You can't plug those values into the original function. These values aren't in the domain of the original function, right? So that's always bugged me. So there is a different algebra you can do, which is the following. You can multiply this out, right? So you end up with like ax squared plus bx squared plus cx squared, right? And are there any x squareds over here? So therefore, you know that a plus b plus c has to be 0. So you can generate 3. Then you look at the coefficients of x squared, which is 0. You look at the coefficients of x. You look at the constant. You can set up 3 equations with a, b, and c. And you will get the same answer, but it's much longer. It's a pain in the butt because solving 3x3 systems, not so much fun, right? This works. Did you try doing it? You tried solving a 3x3? Yeah. No, and there are some books that they will only do that. What it's one of those things that it hasn't been too pressing for me because this method, I've never seen it not work. I've always seen choosing magic numbers to work, so I haven't been particularly motivated to find out why it works, even though it seems like it shouldn't.
Yeah.
You understand? Like it's not in the domain, but apparently that doesn't matter. I'm moving on. Okay. You guys, if you want to think about this, please go ahead. It's just been at the back of my mind for a long time. Okay, and you might have thought to yourself, hey, I just learned about partial fraction decompositions. The challenge is, can someone tell me why using PFD on this, it doesn't seem like it's going to work too well? Can someone tell me why? Yeah.
Because the power of x is off by 2.
Well, it's off by 2, so you can't use U substitution, but why can't we use partial fractions on this?
Because it doesn't become a perfect fraction.
What'd you say? You told me the answer, so shh, shh, shh. What'd you say?
Become a perfect fraction.
What do you mean a perfect factor? I like that.
As in, you have to complete the square or something.
Ah, there you go. Good harmony right there. Now here's the thing. Everything is factorable. Is everything factorable nicely? No. So some people said, well, you can't use PFD on this because you can't factor the denominator. Well, you can factor the denominator. It's just not very nice, right? You can. It's just not nice. So you might want to look for another method. So on this one, let me show you a really cool mathematical trick. And it's completing the square, but a little creatively. Here's the thing you have to realize. X squared plus 2x plus 2, that's the same as x squared plus 2x plus 1 plus 1. This is kind of cool. Usually you have to like add and subtract the same thing. But what is x squared plus 2x plus 1? Plus 1, right? We haven't changed anything yet, right? So you can rewrite this as 1 over x plus 1 squared plus 1 dx. And now, don't say anything out loud. Can you tell me what that looks like? Raise your hand if you know what that looks like. What's it look? We've already actually seen
Oh,
this.
wait.
Ali has come to a realization. Nasher Shama. Nasher. Yeah, it is. But here's the thing. There's only one change in it. The x plus 1. So theoretically, you could use U substitution, but you can just do this one because the change, because x has a coefficient of 1. This is just equal to what? Tan inverse of x plus 1 plus c. And you're done. I don't know if I pointed it out. So we're in G period notes right here. If you go back to the notes from the day before, did you see what I put at the end? Wow. All the work for 15 is there. So you can take a look at this. I don't want to write it out again. It's relatively straightforward. It's just, let's pick something that I didn't paste already. You can take a look at this. So let's go back and not do 15, but does someone have a question like 15 that you want to do? 10? It's okay. It can still be one that we want to do. You want to do 10? Sure. Let's do 10. It's fine. Some of the easiest ones to write can be really annoying. So what does it ask us to do for this one? It says The comparison test? Yeah, so for the comparison test, you want to find something that it's greater than that blows up, or that it's less than that converges. So when we look at this one, did anybody come up with something good to compare it to? Yeah, we have to compare this to something. What are we going to...
I did compare it with ln of n.
You just compared it to... Oh, you compared 1 over ln n to just ln of n?
Yes.
Oh, cool. Okay. So so this is n goes to infinity, right?
Right. So 1 over ln has to be smaller than ln of n.
It does. That's correct. But this blows up. You just showed that it's less than something that blows up. Does that tell us anything? No. Yes, that's correct. 1 over ln is going to be less than ln because ln gets huge as n goes to infinity. But you pick something, it's less than something that blows up. That doesn't tell us anything concretely. So we need to pick something that 1 over ln is convergent, that it's less than or greater than something that blows up. Did anybody come up with something to compare it to? So let's analyze this. What about 1 over n? Is it greater than or less than? Well, that's you have to be really careful about it, right?
N is greater than
2, right? And also n starts at 2, right? So it's challenging because, like, what's the natural log of 2? Do you understand what I mean? That's why it's hard to remember these things, right? You could use a calculator to estimate it, but here's my question. Let's devolve this. The comparison right here, it is smaller than 1. That's true, but if you plug in 2, it needs to be... The comparison we need is this. ln of n compared to n. How do these things compare?
It's smaller than.
Is this true? Is this always true? No. Well, let's think about it. Let's just try it. ln 2 is less than 1, right? Yes. So when you plug in 2, it's definitely true, right? What about 3? Yes. Definitely, yeah, it's definitely true. What about 4? What about 4? ln 4?
Isn't the purpose of logging something is to make the number small?
It depends on what you're plugging in.
Oh,
It totally depends on what you're plugging in. The point is, okay, so I believe that's true. Is that true?
Oh no, yeah.
Is that true?
No.
It's always true.
I think it is.
Because
I think it's always true.
ln of 100 is still
really small. Yeah, ln of 100, it's small. It's real. So I think this is true, but let's see what this tells us. So if that's true, what does it tell us about 1 over ln of n compared to 1 over n? It's got to be bigger, right? Do you agree with that? And is that what we want? Yes, it is. Because what's the sum of this? Blows up, right? So therefore what does this have to do? It has to blow up as well. We just showed that it's greater than something that blows up. Does that make sense? Simplifying factorials. Please simplify what's inside the parentheses first. Please simplify what's inside the parentheses first. So on the top, what do you end up with? 2n times 2n minus 1 times, right? You see this?
Oh.
Over. I said simplify the other one first, though, right? So what does this become? 2n plus 2 factorial. So what's the next one? 2n plus 1, 2n, and then what? 2n minus 1. You with me so far? And this is the limit as n goes to infinity, right? Now do we get a bunch of things that cancel? Oh, this goes away, right? So what are you left with? The limit as n goes to infinity of 1 over 2n plus 1. And as n goes to infinity, what does that go to? 0. It goes to 0. So therefore this what? Converges. Because the limit goes to something less than 1. Okay. Yay! Really cool. Okay. First of all, I'll just ask you questions to direct you. Or I can ask you one general question first. When you look at that, the comparison test is like you get to sand, right? Remember how I talked? You get to like eliminate things and make it bigger or make it smaller. So remember, we want this to be less than something that's convergent or greater than something that's divergent, right? So there's something kind of cool. The first thing we can look at, this right here. What do you know about that? What's the biggest it can be? The biggest it can be is 1, right? And what's the smallest it can be? The smallest it can be is -1. So it can go in between, but it's squared, so it has to go between what and what? 0 and 1, right? So sine n squared, or sine squared n, it's the same thing, with the parentheses. Can it ever make the thing bigger? No. It either stays the same or makes it smaller. So here's my question. N times sine n squared over n cubed plus 1. How does that compare to this? How does that compare?
Small or equal.
It has to be less than or equal to. Do you agree? Because if you get rid of it, you can't make it bigger with that thing. So if you get rid of it, it's only making it smaller. Does that make sense? You're getting rid of a thing that can only make it smaller, so therefore the only thing you can do. Okay. Now, does it become more clear? Now, this right here, when you take away the 1, so if you make the numerator, if you make the denominator smaller, how does this compare? N over n over n cubed. I just got to actually write what I'm saying. N over n cubed. How does that compare?
Bigger.
It gets bigger, right? Do you agree?
Yeah.
And what is that equal to?
N squared.
1 over n squared. But what do you know about this? Converge. So therefore this what? Converge. Kind of cool, huh? On a test, I'd really like you to write at least like one sentence or one proper phrase. I am paraphrasing right now, but you would need to say, just so you know, this right here, we've just shown that n sine squared n over n cubed plus 1 is less than 1 over n squared. Therefore, this has to be true right here. And because we know that, what type of series is this? What type of series? It's a P series. I was about to write Peries. P series with P greater than 1. Therefore, it what? Converges. So therefore, the thing that's smaller than it has to converge. Mm-hmm. Yeah. This right here, just the visual. When you look at this, so let's say I just flash this on the board. What emotion do you first feel when you see this flashed on the board? I'm serious. What emotion? What's like the first emotion that comes to mind? Awful. Totally fair. It does. No, don't understand it. I just want you to look at it from like a visual, artistic sense.
No, it's not pretty.
It's not pretty. Oh, I admire the symmetry.
There's some neat symmetry. There's some cool things to it, right? This phrase right here is something that's important that I can pretty much guarantee you will need to know for at least 1 or 2 questions on the BC calculus exams. But what's really nice about this is this really cool ratio that it has. It looks terrible, like if you had to give it a numeric rating for how terrible it looks, like up here, right? In terms of how difficult it is to use, this is about as easy as it gets. Here's what it says. Let's disassemble what it says. It says, let Sn be the partial sum of this n, right? It's an alternating series. What does this thing do right here? The -1 to the I minus 1. What does that do?
Just like this one.
Yeah, it makes it just go back and forth, right?
I like that.
So why are they using I all of a sudden? That's a good question. You can use any variable name you want for your index variable. I think it's a terrible choice because I has an intrinsic value. Like it's not. This is just.
I thought
Wait, why? Why? They're like they needed to use another one because they were using an for something else, so they chose another letter and they chose I. For no reason, just to piss us off, okay?
Because I was thinking.
Yes, no, you're like that doesn't make sense. So all this does is flip the sign. That's all it does. This right here is the actual term, be the nth partial sum. So S1 would be just the first number. S2 would be the first 2 numbers added together. S3 is the first 3 numbers added together. And S is the limit of the partial sums. So S is just the sum if you took them all. That's what we've been doing, right? We've been finding a lot of those. So that's the first line. That's just defining our variables. Suppose that, this is important, an plus 1 is always greater than 0 and less than the one before it. So basically it has to look like this. This alternating series is going to go like this, but it's going to get smaller and smaller.
Like the thing we had.
Yes, around 0. So visually, what does it look like? The series has to look like this. It's going to go like this. It's going to get closer and closer. You see what I'm drawing there? So the distance, do you see this distance from 0? That distance from 0 has to keep on getting smaller and smaller, even though it gets pretty not super accurate right here. Okay, I'm just going to erase that. Do you understand what I'm trying to draw right there? So there's a qualification. The qualification is it has to funnel its way to 0 going back and forth. Here's what's really cool. This phrase is super cool. It looks weird, but it's super cool. Again, what's S?
The sum.
S is the actual sum, like the real sum. So like, what's 1 plus a half plus a fourth plus an eighth? 2. You can add it all up and get it. You know that the limit is 2, right? S is the actual sum, right? Like if you did the limit, the partial sum is Sn, right? When you take the absolute value of two things, that's the distance between them. This is also known as the error between what you have and where you're going. Calculating errors is really important. You want to know, like, if you're as you add together more and more partial sums, like the partial sum S7, S8, S9, theoretically you're getting closer and closer to the actual sum of the infinite series, right? You might want to know, okay, if I've gone 9, S9, what's the maximum error of that estimate? Comparing it to the actual limit right here. This is what's really cool. The error is at maximum equal to the next term in the sequence. Let me show you. I'll show you the picture. It should make visual sense, but let me show you what I mean. Alternating harmonic. What does the alternating harmonic series look like? It's 1 and then what? Plus what? Minus. Plus. It keeps going, right? We know that's an alternating series. It's going to 0. So does this converge or diverge? Do you remember? We talked about it last class. It does converge. This was the cool example where this right here converges, but if you take the absolute value, does it converge? No. So this is called conditionally convergent. This is conditionally convergent. We're getting to that. So this is convergent, but the absolute value isn't. But let's take a look at this. Does that series fit this? Does the absolute value of each term get smaller? Do the terms tend to 0? Do they go to 0? Yeah, they do. So we can apply this. S1 in this case is 1. S2 is 1 minus a half, which is what? 1 half. S3 is 1 half plus 1/3, which is what? 5/6. And S4 is 5/6 minus a fourth, which is what? Can you do it? 14 over 24, 7/12. Are you? So the partial sums, you're like, oh, I don't know, but I'll believe it. This one, those are the partial sums. You with me so far? S. The maximum error of S4 is going to be 8/5, which is 1/5. So this right here is within 1/5 of the actual sum. It's pretty cool. What this theorem says is if you have an alternating series that's going to 0 like this, if you want to know what the maximum error is at Sn, the maximum error of Sn is bounded by just the next term that you would add next. So what's the maximum error? What's the maximum error right here at 5/6? No, just 1/4. You don't look at the negative. It's 1/4. The maximum error when you're at 5/6 is 1/4. What's the maximum error at 1 half? 1/3. What's the maximum error here? A half. What happens to the maximum? As you expect, as you take more and more terms in the partial sum, do you get closer or farther away from the actual sum? Closer. So theoretically, the error would be better to have error that's smaller. As these terms go on, by definition, we couldn't have used it unless they get smaller. So these dictate the error that you have. So the farther you go, the closer your error, the smaller your error is. I can almost guarantee you're going to get at least one multiple choice question that you're going to look at and be like, for a millisecond, you're going to be like, and then you're going to realize, oh, I just need to calculate the sixth term. The question you will see on the BC calculus exam will literally be, here's a formula for AN. AN is some horrible thing, right? And it's going to ask you, what's the error bound, or like, what's the maximum error of the 11th term, of S11? All you have to find is A12. That's it, and then you're done. That's it. We don't prove this, but visually, what does it look like? All of these terms are alternating, right? These terms are alternating, and they're getting smaller. So theoretically, think of it this way. If you started at 0 and you added 1, you would go to here. But then if you took away a half, what happens? You would go back to here, correct? And then if you added a third, where do you get to? There. And then if you take away a fourth, where do you get to? A smaller amount. So do you see what's going on? If I go one step this way, but then a half back, and then a third forward and a quarter, it vibrates around where you're going, right? The maximum error is the farthest. So what's the actual sum? Where does the actual sum live? In the overlap. The actual sum is somewhere in here, right? Do you agree with that? Because it's going back and forth around it. It's greater than, it's less than, it's greater than, it's less than. But what's the furthest you could ever get away? The next term. The furthest you could ever get away. Because look, if I'm at 1, if I'm at 0, I'm going to 1. It's an overestimate, right? And then it's an underestimate, and then it's an overestimate, and then it's an underestimate. But every time I move, I only can move as much as the next term. So this, you don't have to understand the deep proof, but just understand that you're going back and forth really small. The error is the next term. That's all you need to get from this. So we just looked at it. What's it called? That's the alternating harmonic. Yeah. So this right here is the last piece on 9.4. Absolute and conditional convergence. Absolute value convergence means that AN has to be convergent. Some people ask, well, what about the opposite? Well, the opposite is not necessarily true. The best example you have of that is the alternating harmonic. The alternating harmonic series converges. But if you take the absolute value of each of the pieces and add them together, what happens? It blows up, so therefore it's conditionally convergent. What do you think you're going to see more of in general? Absolute. In general, you'll see that unless you're in a section like this where it specifically sets you up and try to figure it out. In alternating series, how do you know if an alternating series converges? You remember? If it tends to 0. If an alternating series tends to 0, it converges, right? Do we have such a simple test for a series in general? No, we don't. We don't. We have a ratio test, an integral test, a comparison test. We have lots of tests. We have lots of tests. One of the hardest things you have to learn is which one to use when. So some of the questions you get will be, use the ratio test, use the integral test. And sometimes it's going to be, does this converge? And then you have to choose. And then you have the challenge of the plethora of choice. What's the first term of this one? Say n is 1.
Negative 1/2.
Negative 1/2 plus what?
Negative 1/4.
No, it's plus a fourth, right? Minus what? 1/8. No, not eighth, not an eighth. 6. No, I got that wrong. That was me. 6 plus what?
1/8.
Minus
1/10.
So you look at this and you say, man, how do I know? Well, first of all, it's alternating and it goes to 0. So this, as stated, does this converge?
Yeah.
Yes, it's alternating and it goes to 0, so it converges. The real question is, if you absolute value all of this, does it converge? What do you think? What does it almost look like?
1/10.
It almost looks like it. What can you factor out of this?
A 2.
Yeah. So look, what do you actually see right now? So if you did this, right, that's the same thing, right? But if you take the absolute value, what does it become?
1/n.
Of 1 over n. And what does that do? Diverge. All you have right here is half of the harmonic. If you have a series and it converges or diverges and you multiply it by a constant, can the multiplication of a constant change the divergence or convergence of a series? No. So all this is the harmonic series obfuscated by the number 2. That's it. So when you look at these tonight, you'll see ones that look pretty nasty. Keep in mind what the rules are for what you get to play with. What the rules are for what you get to play with, okay?